So here we are on the stationarity tab. What do we need for an ACF to really tell us about predicting tomorrow based on today and yesterday, etc.? We need something called stationarity. The ACF uses correlations, it's in the name. When computing a correlation, we subtract the mean from and divide by the standard deviation for each variable. For a simple scatter plot, the correlation is 1 over n times the sum of the quantity xi minus x bar divided by the standard deviation of x times yi minus y bar divided by the standard deviation of y, x bar meaning the mean of the x values and y bar the mean of the y values. But what if there's no one value of the mean or the standard deviation for a variable? There's trouble if the mean or the standard deviation is different at different time points. And the correlation behavior at any lag should be the same regardless of when it is in the time series. Otherwise, the concept of ACF at lag of whatever doesn't even make sense. It would be different values at different times. So what we'll call a stationary time series always has the same mean and same standard deviation and correlations at every time point. The mean and standard deviation and correlations are not changing with time. Things that don't move as time goes on are called stationary, right? The time series with trends or seasonality or cycles have a mean that changes with time. That's why we focused on detrending and deseasoning or doing seasonally adjusted methods. Now, I'm not saying to never run an ACF on data with cycles. It can actually help you figure out the cycle length if you don't know it. It just doesn't tell you about predicting tomorrow based on today and yesterday. Now, are there time series that have a constant mean but changing standard deviation? Yes, and they're fairly common. We've already seen some. When you take differences of the US Census, the jumps are small for earlier time points when the population is small, and usually larger for later time points when the population is large. So what can you do in that case? Well, you can try using percent change instead of just plain subtracting, or you can try taking the log of the original y values before subtracting. It turns out those two options, percent change or taking logs and subtracting, turn out to be quite similar, since the log of y2 minus log of y1 can be rewritten as log of y2 over y1, and dividing y2 by y1 is the first step in computing percent change. How about autoregressive processes? AR1 is stationary if the absolute value of the A1 coefficient is strictly less than 1, not including the equals 1 case. The A1 equals 1 case is called a random walk. If your estimate of A1 is near minus 1 or plus 1, like 0.98 or negative 0.98, then you should try differencing the time series and then re-estimating A1 to see if your estimate of A1 backs off from the brink of being non-stationary. A new vocabulary term that we'll be using is white noise. Another way to think of it is an AR0 process. YT equals just noise, independent from time point to time point, not dependent on the previous time value, and all the same distribution. So that's called white noise, because if you take its Fourier spectrum, it has equal power at all wavelengths, just like white light does. White noise is the ultimate in unpredictability. The best prediction you can give is just its mean. If you've been analyzing and you get down to white noise, you're done. You can go no further. One last thing, technically what I just defined as stationary, always the same mean and standard deviation and correlations, is actually called weakly stationary. To be strongly stationary, the distributions and joint distributions have to always be the same. For example, normal distribution versus heavy-tailed, but we're not going to worry about that stuff. Let's talk about causation on the next tab. Correlation is not causation. Hopefully you've heard that and understood it before. Just because two things are correlated, that doesn't mean that one causes the other, even when one of them always comes first. So here's an obvious example. Every year my family sends me birthday cards a little bit early, and then my birthday happens. Cards cause birthdays, right? Well, maybe not. So correlations, even large ones, even autocorrelations, can be caused by some outside factor that isn't in our study, called a lurking variable. And so you just can't conclude causation when you see a correlation.